Start this. All right, just reminders, I told you last class that the problem set and the exam, I think I said are due the 22nd, which is a Friday. But I will give you the 20th, which is that Wednesday beforehand, to finish up the assignments if you want to do them a little bit before the 22nd. So we will not have class on the 20th, Wednesday the 20th. I'll remind you again as we get closer, but we will not have class on the 20th. Okay, are there any questions before we start? Anyone look at anything they want to go over? You can always email me too if you'd like. Okay, so we are on page 22. So last class we talked about word problems and how to apply linear equations to word problems. Now we're going to switch back to graphing. I told you we're going to start graphing linear inequalities, which are 95% the same as graphing equations. There's just one extra step. So before we get into that, let me go back and just review real quick the 5 inequality symbols. Well, first off, we have the equal sign, which just means both things on either side of that is equal. We have the less than sign. We have the greater than sign. And then we have the less than or equal to sign and the greater than or equal to sign. And then this one we won't use, but there's also not equal to, just an equal sign with a slash through it. So basically what I'm saying, the difference between less than and less than or equal to, or greater than and greater than or equal to, is that whatever you're talking about. So if I said X, I'm solving for some equation, I get X is less than 4. That means X can be anything up to, but not including 4. Okay. If I say X is less than or equal to 4, that means X can be up to and including 4. If you think about it this way, I will draw, give me 1 second. Okay. All right. So let me do this. This is my backyard. Whoops. And next to me is, let's see here, Nayeli's backyard. Oh, yep, there we go, Nayeli's yard. So I just moved in, okay? And I noticed that Nayeli has fenced in her entire yard. So she has a fence going all the way around her yard. Here's her house. Here's my house. So if I'm talking about Nayeli's yard, Nayeli owns everything between these two fences. And she also owns the fence herself. So the boundary of her yard is part of her property. So her property, we'll just do this. Doesn't really make tons of sense in terms of yards, but it's going to be greater than, less than or equal to. Because she owns the boundary, we include the equal to. Okay. My yard, I put a fence around the back. I don't need a fence on Nayeli's side because she already put up a fence. So my yard, I own up to, but not including. I own every blade of grass up to Nayeli's fence, but I don't own the fence. So then this would just be less than. Okay, they're almost the same with the exception of one specific value, namely the fence itself. Okay, and when we graph, we're going to use a different type of line to determine which one of these things I'm talking about. But again, if you own or the boundary is part of the solution or part of the graph, it's going to be less than or equal to. And if it's not, it's going to be less than or greater than. So we have additional steps for graphing inequalities. Before I write the additional steps, I'm just going to start by writing graph. Whoops. a normal line. That'll be step 1. Let me make this smaller. We're going to graph it like a normal line. If we have the inequality of less than or greater than, we use a dotted line. We're going to use a dotted line to represent the fact that we're not actually including the boundary, that you don't own the fence. Okay, you own up to, but not including the fence. So there's still a boundary there. It's just not part of our solutions. If the inequality is, I don't know how I could copy that. Let's just do it like this. I'll just write it in. We use a solid line. So let me write that in because I don't feel like copying the logo, the symbol. If less than or equal to or greater than or equal to, we use a solid line. So basically, we're just building the fence. So then the last step is to figure out which side of the fence is my solution. Okay, which side of the fence contains the points that is a solution to this inequality? Well, then we're going to use a test point. Use a test point. And that's usually going to be 0, 0 to see which side of the line to shade. And I'll explain that again in just a second. But we're going to graph just like a normal line. Let me change the color so you can see that better. We're going to use, if it's less than or greater than, we're going to use a dotted line. If it's less than or equal to or greater than or equal to, we use a solid line. And then we're going to use a test point, usually 0, 0, to see which side of the line to shade. So I'll leave that up there for you to copy one more second. Then I'm going to go back and explain something else. I think when we first started talking about graphing, I gave you an example like this. I said something like y equals x, let's just do this, plus 2. And I'm going to graph that. So I'm going to start my y-intercept, which is 0, 2. And then I'm going to use my slope to find a second point. My slope is 1 or 1 over 1. So I'm going to go up 1 over 1. So I'll connect those 2 points. Let's change that to blue, just like that. So I told you before, maybe multiple times, that this graph represents every single XY combination that lets this equation be true. So in particular, if I want to talk about a specific point, I could say, all right, if I have the point here, let's say this is the point 5, 7. When x is 5, I get y is 7. So 5 plus 2. So that point falls on my graph. Now, if I change my equation into an inequality, I say no longer does y just equal x plus 2. Y could be greater, y could be greater than or equal to x plus 2. So y can be equal to x plus 2, or y could be larger than that. So the 0.57 still works because 7 is greater than or equal to 5 plus 2. But now this point also works, 5, 8. Because 8 is greater than 5 plus 2. This point also works, 5, 9, 5, 10, 5, 11. Those all work. So all the points on the blue line still work, as well as all the points above it. So you should notice that this entire side of the blue line works. You can pick any point that falls on the blue line or above it, and it will satisfy this inequality. So before, our solution to an equation was just the line. Now our solution to an inequality is going to be an entire region of the graph. All right, so we're just going to follow these 3 steps. It's not that difficult. We're just going to start by graphing it like a normal line, which basically means I'm going to replace the inequality with an equal sign. So I'm just going to graph it like a normal line. Then I'm going to worry about if it's dotted or solid, or if which side I shape. So this says graph y is greater than or equal to 1. So I'm going to just change the inequality and just say, all right, let's graph y is equal to 1. So if you remember from 2 classes ago, y equals something, this is going to be a horizontal line. From that vuxoid, I gave you that word, vuxoid. All right, so I'm going to graph a horizontal line at y equals 1. Here's y equals 1 right there. Now, since it's greater than or equal to, and not just greater than, we're going to use a solid line. So I'm going to graph a solid line at y equals 1. Now, this would be the answer if I was graphing y equals 1. But I'm graphing y is greater than or equal to 1. So you might be able to tell just by the inequality symbol, but I'm going to pick a test point anywhere I want on the graph to see if it works or not. If the test point works, then we know the side the test point is on is our solution. If the test point does not work, then we know the other side of the line is our solution. So we're going to test the point 0, 0. 0, 0 is always the best point to test. The only reason why you would use a different point is if for some reason our line goes through 0, 0, the origin. But it doesn't here. 0, 0 is right there. So I'm going to test 0, 0. There's nowhere to plug in an x value. So I'm just going to plug in 0 for y. I get 0 is greater than or equal to 1. 0 is not greater than or equal to 1. This is false. So this point doesn't work. So the bottom of the line is the wrong side. So I know that I should be shading the top of the line. So my solution set is going to be the line and everything above it. Okay. Any questions on that? It becomes easier once we do regular examples, not these weird horizontal and vertical lines. Let's try this one. So this says graph x plus 2y is greater than 4, but I'm just going to graph x plus 2y equals 4. This is in standard form. So I'm going to graph it using intercepts. So the first thing I'm going to do is find the x intercept. So I let y be 0. I'll write this down here. Y equals 0. So I get x plus 2 times 0. X plus 2 times 0. 2 times 0 is just going to go away. So I'm just left with x is 4. So I get the coordinate x is 4 when y is 0. 4, 0. 1, 2, 3, 4. Now let's do the y-intercept. We'll let x be 0. Always let the other variable be 0. So I let x be 0. this just becomes 0. I'm left with 2y equals 4. Dividing both sides by 2, I get y equals 2. So I get the coordinate when x is 0, y is 2. Graphing that over 0 up 2. I am right there. Now I can connect my two intercepts with a, since this is strictly greater than, this is going to result in a dotted line. Because points on the line no longer work. All right. I'll show you in just a second once I graph it. So I'm just going to do a dotted line. I can just make mine dotted, which is very nice. All right. And like that. So these 2 points are on the line. So if I plug those in, they shouldn't work because we said points on the line don't work. Let me plug in 4, 0. So I plug in 4 for x plus 2 times 0. Is that greater than 4? I get 4 is greater than 4. Look, that's not true. 4 is not greater than 4. So points on the line don't work. That's why we made it dotted. Now I need to figure out which side of the line is the answer. Is it above the line or below the line? Don't try and say, oh, because it's greater than it's always going to be above, or if it's less than it's always going to be below. You have to also watch the signs. So it's always beneficial to test 0, 0. So we're going to test 0, 0. I'm going to test this point right here. So when I plug in 0, 0, I get 0 for x plus 2 times 0 is greater than 4. 0 plus 0, I get 0 is greater than 4. 0 is not greater than 4. This is false. So this point doesn't work. This green 0, 0 does not work. So that means that I should be shading the other side of the line, not this side, not below it, but above it. Any questions on that? All right, moving right along. After we do a bunch of examples, I'll show you how you have to graph it on MyMath. Can be a little tricky. All right, another example here. Negative x plus 2y is less than 2. I'm going to graph negative x plus 2y equals 2. Standard form. So I'm going to find the x-intercept and the y-intercept. I'll do y-intercept first. So I let x be 0. So I get negative 0, which is just 0, plus 2y equals 2. Dividing by 2, I get y equals 1. So when x is 0, y is 1. So I get the coordinate 0, 1. 0, 1, we're going to go right there. And this guy now, we're going to find the x-intercept. That's what we get when y is 0. So we plug in 0 for y, I get negative. Don't forget your signs. Negative x equals 2. So when I divide by negative 1, I get x equals negative 2. So when y is 0, x is negative 2. So I have the coordinate negative 2, 0. Plotting that, -2, 0 is right here.
I have a question.
Yeah.
So in this case, when you're dividing with the signs and it's negative, you don't have to flip the sign.
So remember, the first thing I did was change this to an equal sign. I only
Okay.
really look at this when I'm testing 0, 0 and when I'm plotting the line. Is it dotted or solid? So if I did keep this sign, yeah, you would flip it. But I
Okay.
switched it to an equation just to figure out where my intercepts were. And then I'll go back and figure out, is it dotted or solid? Does that make sense?
Mm-hmm.
Yeah, you're absolutely right. If I was solving this equation with an inequality, you definitely need to flip the sign. But I'm saying, don't even worry about that right now. I'm just looking at where the boundary is. So I'm going to treat this like an equal symbol. So we don't have to worry about flipping it. So now, after I have my intercepts, now I want to check, okay, is my line going to be solid or dotted? Well, since this is just less than, it's going to be a dotted line. So I'm going to connect those two guys with a dotted line. Still dotted. There we go. Okay. All right. So now I need to test 0, 0. Figure out which side of this boundary is my answer. Test 0, 0. So I'm going to plug in 0, 0 into the equation. I get -0 plus 2 times 0 is less than 2. So now I am concerned with the symbol. This is just 0. This is just 0. So I'm left with 0 is less than 2. Oh, finally. So 0 is less than 2. This is true. So now this point works. 0, 0 does work. So I know my solution is going to be the side that 0, 0 is on. So I'm going to shade the part below it. So any point in this green area will satisfy this inequality. Okay, let me know if there's any other questions. All right, let's try this one. Graph y is greater than or equal to 2x plus 7. Now we're in slope intercept form, no longer standard form, but the process is the exact same. I'm going to start by graphing y equals 2x plus 7. Right, this is in slope intercept form. So I know my slope is 2 or 2 over 1. And my y-intercept is going to be 0, 7. It's always 0, that guy. So these are actually a little easier to graph. I'm going to start at my y-intercept 0, 7 over 0 up 1, 2, 3, 4, 5, 6, 7. And since my slope is 2 over 1, I'm going to go up 2, 1, 2 over 1. So I'm right there. So I can erase those jump marks. I don't want to get too confusing here. So there's my 2 points. And now I'm going to graph them. I'm sorry, I'm going to connect them since it's greater than or equal to with a solid line. So go to my line, change it to solid. Connect those guys. Okay. Really, I guess this should keep going down, but whatever. All right. Now I don't know if it's this side or the left side, so I'm going to test 0, 0. Test 0, 0. Plugging in 0 for y and 0 for x, I get y, or 0, is greater than or equal to 2 times 0 plus 7. I get 0 is greater than or equal to 0 plus 7. 0 is greater than or equal to 7. 0 is not greater than 7. So that's a false statement. This point does not work. So this is the wrong side. So I'm going to shade the other side of the line. Okay. Let me know if there's any questions at all. All right. Now I'm going to, instead of this, I'm going to pull up some math questions. Linear programming, graphing linear inequalities. So let me. Okay. Oh, this is a good one. Okay. Let's do this one. Because this is good practice, and I want to show you how the heck you graph these things on a on math. Okay, we'll start with them. All right. Okay, so I have this equation: y minus 1/2 x is less than or equal to 2. So you can do this two ways. You could, if you don't like this fraction, you could start by multiplying everything to get rid of it. You can leave it there and just mess with it when you're solving for something. You could get this to be in y equals mx plus b form. There's definitely more than one way to do this. I'm just gonna leave it go. Actually, now let's get rid of it first. So just like we did in the very first day of this chapter, I said, if you have a fraction in your equation, always start by getting rid of it, just like we do with parentheses. So if I want to get rid of this 2 on the bottom, I'm going to multiply the whole equation by 2. I'll show you how there's more than one way to go about this, but I'm going to multiply this whole thing by 2, every term in the equation by 2. So I end up getting 2y minus 1/2 times 2 is just going to be 1x is less than or equal to 2 times 2 is 4. Okay. What else could you have done? Let me do this in a different color because I can come back to it later. If I wanted to solve this for y, so it's in slope intercept form, I could have just added 1/2 x to both sides. So look, I get y is less than or equal to 1/2 x plus 2. Now, it might not look like it, but these two equations are the exact same line. Okay. I'll graph the green and then I'll show you that it's the same as the bluish color. So what I'm going to start by doing is graphing 2y minus x equals 4, just like I did in the last 4 examples. Change it to an equal sign. This is in standard form. So I'm going to find the y-intercept by letting x equal 0. And I get 2 times y minus 0 equals 4. Dividing by 2, I get y equals 2. So when x is 0, y is 2. Now the flip side of that, I'm going to find the x-intercept. That's what we get when y is 0. So I'm going to let y be 0. I get 2 times 0, which is 0, minus x equals 4. Getting x by itself, divide by -1, you get x equals -4. So when x is -4, y is 0. So it helps to kind of draw a picture of this somewhere before. It doesn't have to be a perfect graph because you can't plot the points on the graph. Well, you can, but I'll show you that in just a second. So I'm just going to copy this stuff over to here, and then I'll show you how to graph it on my map. So I'm going to plot my y-intercept, which is 0, 2, which is right here, and -4, 0, which is right there. So these are going to end up being connected by a solid line because it's less than or equal to. So I'm going to take that, connect that, bada boom, bada bing. Move this down there. Okay. So there's my boundary. So now am I going to graph above it or below it? I'm going to test 0, 0. I get 0 for y, 0 for x. I get 0 times 2 minus 0 is less than or equal to 4. 0 is less than or equal to 4. This is true. So we will shade the 0, 0 side. So my answer is going to be a solid boundary line and everything below it. Going back to this other way I solved it, this one right here, this would start at y equals 2, 0, 2, and we would go up 1 over 1. Well, look, 0, 2 right there. We would go up 1, not up 1 over 1, sorry, up 1 over 2. So it doesn't matter which one you use to graph it, they're both going to work. Okay, so I have to translate this to my MyOpen Math. I'm going from -4, 0 to 0, 2, and I'm shading below it. How do I do that? Let's go back up and find that one I just did. Right here. So the first thing I do is select solid or dotted line. We said it was a solid line. And our line goes from -4, 0. So I'm just going to, let me make this a little bigger. I'm just going to go from -4, 0, click on that, boom, to 0, 2, put it right there. And then you'll see after I click that, if I scroll below it, it shades below. If I scroll above it, it shades above. You're just going to go down here. It doesn't matter where you click down here. You could just click on the origin because that's the point you tested. Click that, and that's it. If you keep clicking, it's going to mark it wrong. So you're just going to do your intercepts and then 1 point on the correct side. And you should see, hey, I got it right. Okay. It can be confusing. Click your intercepts, hover your mouse over the correct side, click, and that's it. Any questions on that? Okay. Let's try this one. Ooh, a little uglier still. But we're going to use the same technique we did on the last example. I want to start, I'm going to rewrite this. X divided by 5 plus y over 3 is greater than 1. I want to start by getting rid of the fractions. So the problem is, up until now, we've only dealt with equations that had, or inequalities that had one denominator. Here, this equation has two denominators. It has 5 and it has 3. So I can't just multiply this thing by 5. I can't just multiply this thing by 3. Does anyone know what number I could multiply this entire equation by so that both denominators go away? All right, beautiful. Cameron says 15. Now, Cameron doesn't have to answer this next question. They can if they want. But what is 15 in relation to 5 and 3? Why did Cameron select 15?
5 times 3 is 15.
That is correct. They both go into it. But what's even extra special about 15?
They're multiples.
Hey, okay, beautiful. Jay, I think that was Jay. Beautiful. What?
Yep.
Hey, there you go. I was getting there.
There you go. Okay.
There you go. The least common multiple. So it doesn't have to be the least common multiple. It's just the, so the least common multiple means the smallest number that 5 and 3 go into. But Jay's right. It could be any common multiple. I could use 30. I could use 45. I could use 60. Any number that they both go into. But Will's right. The least common multiple is usually the easiest just because it's the smallest. So you can find least common multiples in your calculator. I think you just hit math, number, go over to the num menu. And there it is, option 8, the least common multiple. So I'm just going to plug in 5, 3, and you get 15. So if you're not sure why we use 15, you'll see in just a second, but I'm going to distribute the 15 to each term. So I get 15x over 5 plus 15y over 3 is greater than 15. Don't forget to multiply that by 15 as well. And the reason we picked 15 is because now these will reduce. 15 divided by 5. I'm going to put this up here. That is 3x plus 15 divided by 3. That's 5y is greater than 15. So now this is much more doable, right? This is much prettier than this thing. So we can kind of get rid of that. So the first thing I'm going to do is I'm going to graph 3x plus 5y equals 15. Okay. I'm going to do, I'll just kind of do this one quick. We'll do the y-intercept. Let x be 0. This thing is 0, so I get 5y is 15. So y is 3. So when x is 0, y is 3. The x-intercept we get when y is 0. So this is 0, so I get 3x equals 15. So x equals 5. So I get 5, 0. So I'm going to connect 5, 0 right there to 0, 3. These will be connected with a dotted line because it's just greater than. And then we will test 0, 0. Plugging in 0 for both, I get 0 times 3 plus 5 times 0 is greater than 15. 0 is not greater than 15. This is a false statement. So 0, 0 doesn't work. So I'm going to shade above it. So there's 4 things you got to remember. The intercepts, dotted line, shade above. 0, 3 and 5, 0. So let's find that question. It's this guy right here. Dotted line, I'm going to click that first. 0, 3, we said. So there's your y-intercept. 5, 0. There's your x-intercept. Trying to get that as close as possible. And we were shading above it. Any point above it. Boom, just like that. Yep, perfect. Any questions on that? Okay, last one. This just says, is x equals 8 and y equals 10 a solution to each of the inequalities? This is really straightforward. You're just gonna, well, notice the left-hand side, they're all the same. Negative 3x plus 2y, negative 3x plus 2y, negative. So let's just plug 8 and 10 into that. Negative 3 times 8 plus 2 times 10. That's negative 24 plus 20. That's negative 4. So the left-hand side of all of these is going to be negative 4, negative 4, negative 4, negative 4. And then just go, is negative 4 less than 10? Yes. So it's a solution. Is negative 4 less than or equal to 10? Yes, that this is a solution. Is negative 4 greater than 10? No. Is negative 4 greater than or equal to 10? No. Okay, so don't make these more complicated than they have to be. They're relatively straightforward. Now I'm going to move on because we're going to use this in the thing we're going to do in 2 sections, but now we're going to switch gears to solving a system of linear equations. This is a big one. This is going to be used in the final section of this chapter. This will be used if you ever take Math 100. Probably most of you won't. But this is really, really important concept. So we're going to try and take our time, make sure that everyone understands how to do this, because this is really important. Solving systems of linear equations. Now, a system of linear equations is just more than one equation. The first day of class, I think I gave you one that had apples, bananas, and coconuts. There was 4 equations there. That is a system of equations. You use the first equation to find out what apples were. You plug that in to find out what bananas were. So that's what we're going to be doing today. It's just, we're never going to have more than 2 equations. If you go to higher math, like if you ever take linear algebra, you could have 5, 6, 12 equations. For this course, we're only ever going to use 2 equations. Okay. Now, a system is just going to be, you just have 2 lines. So if I'm solving a system, basically, if I graph a line, that's all the points that make that equation true. If I graph another line, that's all the points that make that equation true. So the solution to a system, oh, I don't want to do that. If I just, as an example, graph these 2 lines. Now let's do a red one, like that, and a blue one, like that. The solution to this system is going to be the point that satisfies both equations, or the point that both lines share, or the point of intersection. So this point here is the solution. So a solution to a linear system of equations is the coordinate or coordinates that satisfy all the equations in the system. The coordinate or coordinates that satisfy all the equations in the system. So for the purposes of this course, you really can replace all with both equations in the system, because we're only talking about two. Okay. So there are three different possibilities we could have when solving for the solutions to a linear system of equations. The first one is called a unique solution. That is one coordinate solution. That's basically, let me draw a little picture. That's just going to be, I meant to make that black. That's all right. There's my coordinate plane. Here's one line like that. Here's another line like that. And this is the solution right here. That's a unique solution. Just the one point where they cross. Now, the other possibility is something called an inconsistent system. You don't have to remember the terms inconsistent or dependent. I'll show you how to tell when you have this kind of situation. But an inconsistent system, kind of hard to say, is when there are no solutions. Any ideas how that's possible? I'm looking for the coordinate or coordinates that satisfy both equations. How can I have a system where there's no solutions? My man Will, bringing the fire today too. Yeah, if my lines, there's one, here's two. If the lines I'm graphing are parallel, I'm looking for the point where the lines cross. But if the lines never cross, there is no common coordinate. Okay, and we'll see what kind of happens. You'll kind of figure out through the process of solving it that there is no solution. It works similarly to the way we figured it out in just solving regular equations. Now, the last possibility is something called a dependent system, which is the case where there are infinite solutions. Now, this one's a little trickier, but how can I have a system with an infinite number of solutions? Will's going to go try and go 3 for 3, but this one is trickier.
Multiple points on the.
Yeah, you're right. So there are multiple points. There's going to be an uncountable number of points that fall on both. But how? What would the graph look like? How is that possible? Hey, Will, both equations are the same line. Basically, you have one line, and then you have the other line directly on top. I'm trying to make it so you can still see both lines, but they're the same line. So every coordinate on the first line is also on the second. Again, you will see when we're solving these, how this kind of thing pops up and how this kind of thing pops up. But let's have at it. Just like what we did when we were graphing lines, it depends on how it's written, which will determine which way I'm going to solve it. We're going to learn two methods for solving. You probably remember some of these methods, maybe from high school. The first method we're going to use is called the substitution method. So I'm going to add a little disclaimer here. Oh, no, I'll put it at the bottom because there's the steps at the bottom. Okay. So you're going to want to, when you look at the system, the substitution method we're going to use when one of the equations, at least one of the equations, has one of the variables isolated, has one of the variables solved for. Okay, so don't even worry about the second equation, but notice the first equation has y all by itself. So when you see that at least one of the equations has the variable, one of the variables isolated, I'm going to go, okay, boom, I'm using the substitution method. What do I mean? Like, look at this next example here. On the next page, you don't have to flip it. Notice that the x and y are on the same side. The x and y are on the same side. So none of the variables are isolated. So I'm going to use a different method, the addition method. So I use substitution method when one of my variables in one of the equation or both is isolated. So I have an equation y equals 5x plus 7 and y equals 2x plus 1. What I'm going to do, I can't solve the first equation because there's two variables. I can't solve the second equation because there's two variables. So what I'm going to do is I'm going to take one of the equations where the variable is solved for, and I'm going to take what that variable is equal to. In the second equation, I'm telling you y is equal to 2x plus 1. And I'm going to replace the y in the first equation with what it equals in the second equation. Okay, think back to, let me go back. Right here. Last class. I wrote the equation for duplicate and multiview, and I took what multiview equaled in one equation and I set it equal to duplicate. You're just taking what each equation equals and setting them to each other. Okay, that's what we're doing here. Same exact thing. So I'm going to take 2x plus 1, and I'm going to substitute it into y in the first equation. So instead of y equals 5x plus 7, I get 2x plus 1 equals 5x plus 7. Okay, because this thing right here was y. So now I have an equation with one variable, x. I can solve it. Question? Jay, I think you're cutting out.
For all of these equations
Yep.
that are like, yes. So for all of these equations that are like this, do we all, is it better?
Always, I'm sorry, you cut out again. For all these equations, did you always use what?
For all of these equations, do you always put the second problem like first?
Oh, okay. I
And
see.
then,
So,
like, you see
just
how you use 2x?
follow along, and I'll show you when we do a different example. That's not always the case. It really depends on how it's written. So, like, if I pull up, let me pull up my math just to show you what I mean. System of linear equations. Come on now. Come on now. So, like, we will do one like this. So in this particular example, I have y equals 2x plus 3. You're just going to take what y equals, and I'm going to stick it in the y in the second equation right there. So it's not always taking the second thing and putting it first. What I'm going to do here is rewrite the second equation, but replace the y with this. So I'm going to get 3x plus 6 times y, 2x plus 3. And we'll do another example of this. I'm just showing you that it's not always the case that you're going to make the second thing come first. I'll show you in future examples how it's going to work out. Okay.
Okay.
So just in this particular case, I just took what y equaled in the second equation and plugged it into y in the first equation. So now I have just an equation with x's left. I can solve for x. I'm going to just subtract 5x. I like to get my x's on the left-hand side. So I get 2x minus 5x is negative 3x plus 1 equals 7.
Wouldn't that be -2?
The final answer? Yeah. Oh, yep. You're getting ahead of me, but yep, perfect. I'm going to subtract 1 from both sides. Beautiful. And I get negative 3x equals 6. Perfect. And dividing both sides by -3, you're absolutely right. I get x equals -2. Now, the common mistake students make if we're taking this class in person is they would go, hey, there's my answer, moving on. But that's not the answer. Luckily, on my math, it asks for a coordinate, both x and y. So you kind of know, well, this is only half the answer. I'm looking for the coordinate that satisfies both equations. So I also need y. Think back to those word problems. I have to figure out when you make the same amount of money at each company. And I also have to figure out how much money you make. So I'm going to take the -2 for x and substitute it back into either one of the equations for y. It shouldn't matter because I set them equal to find -2. So I'll plug it back into the second equation. It does not matter which one you plug it into. 2 times -2 plus 1. So I get y equals -4 plus 1. So y equals -3.
Can you do the other one as well?
The one I just wrote down as an example.
Yep. I was just wondering, substitute it back into the first equation.
Oh, this other equation here.
The
Yeah.
X.
Sorry.
Yep.
So yeah, so if I chose the first equation, I'd get y equals 5 times -2 plus 7. I get y equals, this is going to give me -10 plus 7. -10 plus 7, I get y equals -3. So the coordinate will be -2, comma, -3. That's the point where these two lines cross. Okay. Now let's write out the steps. How to solve a system by substitution. Step 1. This is too big. I'm going to use substitution if a variable is isolated in at least one of the equations. Replace the isolated variable with its equivalent expression in the other equation. Solve for the remaining variable. And lastly, use the solution to solve for the original isolated variable. I know it's a lot, but write it down if you want to be able to reference it later. So the first thing we're going to do is use substitution if a variable is isolated in at least one of the equations. We're going to replace that isolated variable with its equivalent expression in the other equation. Solve the remaining variable, and then use the solution to solve for the original isolated variable. Give you a second to write that down. So just to restate what we did here, we're going to use substitution if a variable is isolated in at least one of the equations. The equation here, the y is isolated. So I replaced y with its equivalent expression. Y is the same as 2x plus 1. Replaced y with 2x plus 1. And then I solved for the remaining variable x. And then it says use the solution to solve for the original isolated variable. That's what I did over here in the black and the purple. I used my solution of -2 to solve for the original or the value of y. Now, the first thing you might notice is that this doesn't have any isolated variables. So technically, if I was given this problem on a MyOpen Math, I wouldn't use substitution. Even if MyOpen Math says solve by using blank, you don't have to use that method to solve it. Okay, I will not know which method you use. So feel free to use any method you want. What I'm going to do here is just solve one of the equations for a variable just to show you how to use substitution to do this. So I'm going to replace the first equation. I'm going to change it to x equals 3 minus y. I just subtracted y from both sides in the first equation. So let's get rid of that. So we're just going to pretend like the equation was written, or the system was written like that. We have y plus x equals 5 and x equals 3 minus y. So just like before, x is isolated. X equals 3 minus y. So what I'm going to do is take 3 minus y and replace x in the first equation with 3 minus y. So I'm going to rewrite the first equation, but I'm going to replace that x with its equivalent expression. So the first equation becomes y plus 3 minus y equals 5. Because this thing here was originally x. Okay, if that doesn't make sense, stop me and let me know. But I just took 3, I rewrote the first equation, but instead of writing x, I wrote 3 minus y because 3 minus y equals x. So now I have an equation with just y's left. I have, let's see here, y plus 3 minus y equals 5. I'm going to combine like terms. I get y and negative y. Uh-oh. They cross out. So it looks like I'm left with 3 equals 5. Oh no. Well, this doesn't make any sense.
Wouldn't y be 5 then? 5 plus 3, 8. No, that wouldn't be right.
Right? It's okay that doesn't make sense. It's not supposed to make sense, right? It's completely impossible because this is an inconsistent system. Okay? When you get something like this, some strange thing that doesn't make sense, think back to when we were solving equations. If this was just a regular equation, we would say, oh, this means no solutions. It kind of means the same thing when you're doing systems. This is no solutions as well. All right. Because these lines are parallel. Just to show you, just real quick, so we don't have to do it. If I do x plus y equals 3, x plus y equals 5, there's our two equations, and notice the lines are parallel. They never cross, the red and the blue. So we have an inconsistent system. How would you know the difference between an inconsistent system and a dependent system if there's no solutions or there's infinite solutions? If for some reason I was solving this just like before, and I ended up getting something like 5 equals 5, that would be infinite solutions. So if you get something that does make sense, infinite solutions. If you get something that doesn't make sense, no solution. All right. We'll do more examples, so I'm not going to do that one right now. But so now the second method. What if neither one of the equations has a variable that's isolated? Well, here we have both equations or both lines are written in standard form. I have x and y on the same side. So I'm going to use a different method called the addition method. Sometimes maybe you learned it as the elimination method. Okay. So what I want to do here is I want to, this might sound a little strange, I want to obtain matching opposite coefficients. Matching opposite coefficients in front of one of the variables. So in front of either the x's or y's, I want the same number, but I want them to be opposite signs. Matching opposite coefficients. So notice here, I already have that. I have a positive 2x in my first equation, and I have a negative 2x in my second equation. So that's what I want. I want matching opposite coefficients. Okay, you'll see why, but I want matching opposite coefficients because once I obtain that, if it's not already given to me like it is here, I'm going to take the equations and I'm going to add them together. I'm going to take this top equation and the bottom equation and add them together. Hence the name, the addition method. Now people are like, wait, you can just add equations? Well, yeah, think about it. If I had the equation, a real simple example, I said x equals 4 and y equals 3. I can add these equations together and the answer will make sense. X plus y on the left-hand side, I get x plus y equals 4 plus 3. Well, if x is 4 and y is 3, isn't x plus y equal to 7? Yeah. So I can add equations, and if I do it correctly, the result will also be true. No difference here. It's just you're going to combine like terms. X's with x's, y's with y's, and constants with constants. So you're just going to add, because we're using this method when both of the lines are written in standard form, you're just going to kind of add straight down. Everything should line up, and we're going to add straight down. So the x's with the x's, 2x plus negative 2x. Because I obtained matching opposite coefficients, 2x and negative 2x, they're going to cross out. Gone. Hence the name elimination method or addition method, whichever one you want. Then I have negative 6y plus 4y. Negative 6y plus 4y is negative 2y. Equals 8 plus negative 10. 8 plus negative 10 is negative 2. So I have an equation with just y's left. Divide by negative 2. I get y equals positive 1. But again, that's only half the solution. You need to figure out what x is also. Let's do paint. Brighten it up a little bit. There you go. Let's do that. So I can take 1 for y and plug it back in either equation. I'll plug it into the first one. 2x minus 6 times 1 equals 8. 2x minus 6 equals 8. Add 6 to both sides. 2x equals 14. Divide both sides by 2. X equals 7. So the solution to my system is the point 7, comma 1. Any questions on that? Okay, let me write down the rules or the steps. Step 1, I'm going to do use addition method when both equations are written in standard form. Through multiplication, obtain matching opposite coefficients. Oops. In front, oh, come on now. Either variable. Sometimes one variable will be easier than the other, doesn't really matter. I'll have to make this smaller. Add equations together. Solve for remaining variable. Use solution to solve for original eliminated variable. Make that nice and bold. There you go. Okay. Now, if we look at example B, I don't have matching opposite coefficients. Okay, so I'm going to have to use multiplication to obtain matching opposite coefficients. So you can make a decision here. It's up to you which one you want to eliminate. If you want to eliminate the x's, then you want to get matching opposite coefficients in front of the x variable. If you want to eliminate y's, you're going to get matching opposite coefficients in front of the y variable. Now let's just say I wanted to get rid of the x's. Right? I want to get rid of the x's. What would I do? what would I multiply and by how much? I can't tell if
Not
Brianna,
8, but yeah, 2. There you go. Here on me.
you got the chat box up and you saw what Brianna said?
Yeah, that's why I was like, there you go.
Awesome. Excellent.
Get what I'm trying
Love it. Okay, yeah, multiply the bottom by -2. So I'm just going to write that out. I'll show you. If I multiply the bottom equation by -2, the top one's going to stay 4x plus 3y equals -1. The bottom one, watch your signs, is going to be -4x. -2 times -y is positive 2y. -2 times -13 is positive 26. So when I add these, the x's will go away. If you wanted, you could also multiply. Let's say you want to get rid of the y's. You would multiply the bottom equation by 3. And I'll show you that. If I multiply the bottom equation by 3, the top equation will stay the same. 4x plus 3y equals -1. And this would be 6x minus 3y equals -39. Either way, you're getting these matching opposite coefficients. Okay, so I promise you, if you do it correctly, you're going to get the same answer for both of these setups. It's just whether or not you solve for y first or x first. Sometimes you'll have to multiply both equations by something. If I don't have a multiple here of the other number, the other coefficient, I'm going to have to multiply it. I don't know if there's a preference. I guess we wrote the pink one first, so I'll just stick with the pink. But if you already started doing it the other way, go ahead and finish it, and then we'll compare our answers at the end. So I multiplied the second equation by -2. So now I can just add my equations together. Let me actually do this. Let's see if I can. Nope. I want to select. Oh, that'll work. Just like that. And like that. Okay. So when I add them, 4x and -4x, they go away. That's what I wanted. I'm adding these together. 3y plus 2y is 5y. -1 plus 26 is 25.
5.
Beautiful. Thank you, Jonathan. I think that was Jonathan. 5. We get y is 5. Only half the answer. We still have to use the solution to solve for the original eliminated variable. Again, now there's not really one equation that's easier than the other. They can both be kind of tricky, but I'm just going to plug y into the second equation. But you can use either one you want. 2x minus y or -5 equals -13. I'm going to add 5. 2x equals -13 plus 5 is -8. Dividing by 2, x equals -4. So my solution is -4, comma 5. Any questions on that? Let's see if they have more examples here, or that's word problems. Let's hold off on those. Let's practice some. I'm actually, you can cross out this problem here. And we're gonna use, you can use this space to copy these down. I'm gonna pull up some from my open math. So let's do this one. Oh no, we started that. Let me do a different one. Okay. Current page, we'll do this one too. Current page. And yeah, we'll start with those. Okay, give me 1 second just to set this page up. Down here. Actually, we can just do it like this. There's plenty of space. Okay, and I will cover that up. Nope, nope, nope. There we go. Okay, so these are just 3 examples from the practice problems. It says solve the system of equations by graph. So if you really wanted to, let me go back to this. It doesn't even give you the graph to do it on. So if you, I don't know, want to do it that way, you can. But again, I can't tell which method you're using. So you don't have to use the graphing method. We're not going to use it. I'm going to use since I have y equal to something, y is isolated, I'm going to use the substitution method. So I'm going to take what y equals negative 2x plus 11. And I'm going to substitute it into the second equation for y. Okay, so this becomes negative 2x minus 11 equals negative 6x minus 31. Now I can go ahead and solve this. I can add 6x to both sides. I get 4x minus 11 equals negative 31. Beautiful. Add 11 to both sides. I get 4x equals negative 31 minus 11 is negative 20. So I get x equals negative 5. That's only half the answer. Whoops, don't cover that 31 up. To figure out what y is, you can plug negative 5 back in either equation. Y equals negative 2 times negative 5 minus 11. Y equals, this is going to be positive 10 minus 11. Y equals negative 1. So we have the coordinate negative 5, comma, negative 1. Let's see here. Negative 5, comma, negative 1. Hey, perfect. All right. Now this guy here says solve by substitution. Again, you don't have to use any method they tell you. I am going to use substitution here, but there's not any isolated variables. The y is by itself on one side, but it has this negative 4 here. So any idea what I can do first before I can start the substitution process?
The multiplication method, maybe?
So Yeah, so technically that's what we're gonna do, but it's really weird. We're gonna multiply by a fraction, which is the same thing as saying, I want to get rid of this. I want to get rid of this -4, yeah? So what I can
Yeah.
do, instead of multiplying this by something, I can divide every single thing here by -4. Okay, that's one method. Or you could solve this thing to have X and Y on the same side, and then you could dive right into elimination method. All right, I'm going to stick with this dividing by -4 thing, but just to show you what I'm talking about, if I took the second equation and added 12x, the second equation is going to be, this is 12x over here. It's going to be 12x minus 4y equals -20. And the top equation would be -3x plus y equals 6. Now I have them both in standard form. I can use the elimination method or the addition method. So it's really up to you. Okay, but I'm going to stick with that dividing both sides by -4. So I'll divide this by -4, this by -4, and this by -4. They're all divisible by -4, so it should be nice. So this equation becomes y equals -20 divided by -4 is +5. -12 divided by -4 is +3x. So now I have y equals 5 plus 3x. Whoops. Y equals 5 plus 3x. And I can replace y in the second equation with 5 plus 3x. Or sorry, y in the first equation was y plus 5 plus 3x. So the first equation becomes -3x plus y, but y is 5 plus 3x equals 6. Uh-oh, we get that same situation again. -3x and 3x, they cross out. So this is going to be 5 equals 6. So that means we have no solution. Let's see what our options are here. Where did I put that guy? Yeah, right here. So that's one of our options, no solution. Boom. Hey, beautiful. Okay. And this last one here, question 7, says solve the system of equations by graphing. Not going to do that. All right, but I have everything on one side. I have these constants here as well. I don't want them. I want them to be in standard form, which, if you remember, is ax plus by equals c. So I got to get rid of this -16 on this side, and I have to get rid of this +14 on this side. So for the first equation, I'm just going to add 16 to both sides. First equation becomes 4x plus y equals 16. Second equation, I'm going to subtract 14 from both sides. Subtract 14 from both sides. So I get -2x plus y equals -14. Now I have both my equations written in standard form. So I can get rid of the x's, or I can get rid of the y's. If I wanted to get rid of the y's, I would just multiply one of the equations by -1. If I want to get rid of the x's, I'll multiply the bottom equation by 2. So I'll have positive and -4. So I'm just going to go ahead and do that. So the top equation is still 4x plus y equals 16. The bottom equation is negative 4x plus 2y equals negative 28. Now I can add my equations. So this is 4x, negative 4x. That's what I wanted. They go away. Y plus 2y is 3y equals 16 minus 28. That's going to be negative 12. Solving for y, I get y equals negative 12 divided by 3 is negative 4. So now you can plug negative 4 back into the original, the second original, or these semi-prettier versions. I'm going to plug them into this guy. So I get 4x plus negative 4 or minus 4 equals 16. 4x equals, add 4 to both sides, 20. So x equals 5. So I have the coordinate 5 comma negative 4. Okay, so you've kind of seen every single type there is. I'm going to have you try one. Let me copy this one. I'll copy question 8 from my practice problem. Whoops, I didn't mean to do current page, but whatever. And we'll try this one, question 11. All right, if that's that small, hopefully you guys can still read it. Oh, no, I don't want to do that. These are two of the same. Let me get rid of this one and find you a better one. Come on now. Come on now. Hey, there we go. That's a good one. Okay, so I have two questions. X minus 2y equals 19, negative 5x minus 1y equals negative 40. And I have 2x equals 4y minus 34. And then negative 4x plus 4y equals 48. All right, so you don't have to use the method they recommend. I wouldn't use substitution for the first one. I would use addition. But I'm going to give you a couple minutes. 6 minutes. We'll come back at 9:40. And then we'll share out answers or the methods you used. And then we'll go over the answers and then we'll split. Okay. But I will be sitting here if you have questions. But I want you to give both of these a fair shot. I want to hear from some people I haven't heard from yet. I'm not going to call anybody out, but I want answers from some of our unusual suspects. All right. So give them a fair shot. Okay. Somebody, hope, let's try somebody new or someone who hasn't participated yet. What's the first thing you did for question 11? You can chat it or just unmute and call it out. First thing you do for number 11. All right, now I'll open it up to anybody. First thing you did for number 11. It's okay to be wrong. I'm wrong a lot.
I multiplied the top by 5.
Beautiful. Brianna, thank you. Brianna multiplied the top by 5. Because that way we get, I'm going to rewrite it underneath this one. 5x, 5 times negative 2y is negative 10y equals 5 times 19 is 95. So I have these matching opposite coefficients. Perfect. So I can add these equations together. Negative 5x plus 5x, they go away. Negative 1y, negative 10y is negative 11y. 95 plus negative 40 is going to be positive 55. So dividing by negative 11, 55 divided by negative 11 is negative 5. So y equals negative 5 is our y value. You can plug it back in either one. I'm going to plug it into the first one. I get x minus 2 times negative 5 equals 19. X plus 10 equals 19. Subtract 10 from both sides. X equals 9. So my solution is 9, negative 5. Okay, I mean, if any questions, otherwise I'm going to move on. All right, now there's 2 ways you could have started number 19, and neither one of them is more correct than the other. Does someone want to share what they did for 19? Anybody? Anybody?
I don't think this is right, but at first I did, for the bottom one, I subtracted 4y on both sides so that they can be the same on top.
That's okay. That's so that's perfect. Thank you for sharing. We didn't do one like that yet, but that's completely acceptable. She subtracted 4y from both sides bottom here. So this bottom equation becomes negative 4x equals negative 4y plus 48. Now, I'm going to rewrite this top equation below it. 2x equals 4y minus 34. So even though we haven't done one like this or done one this way, as long as my x's, y's, constants, and my equal signs all match up, x's over x's, equals over equals, y's over y's, constants over constants, I can still add them together. So since no one else gave me any other tips, we're just going to keep going with Brianna's method because I like it. It's fine to do things different way. So I can just add these together now. Something else you could have done to make it look like a question we've done before, you could have subtracted 4y from both sides here. So you'd have negative 4y up here equals negative 34, and then still added them, but we're gonna go with this way. We're gonna go with this method. Just to show you that it will still work. Negative 4x plus 2i is negative 2x equals y negative y, they cross out. 48 minus 34, that's 14. So dividing both sides by negative 2, x equals negative 7. Beautiful, beautiful. Now, to get y, I'm just going to take negative 7, plug it back into either equation. I'll plug it into the first one. 2x, 2 times negative 7 equals 4y minus 34. This is negative 14 equals 4y minus 34. Add 34 to both sides. That gives me 20 equals 4y, or y equals 5. So we have negative 7, 5. Any last questions? Now, I'm not assigning homework, but I really, really highly recommend that you at least try some of the practice problems. And you can do a lot of the problems from your problem set. I don't know if we have the same numbers, but if you go to the problem set, you can do, I mean, pretty much anything up to systems of inequalities. So let's see here. Then we can do that. We can do, yep. Yep, yep. You can do pretty much everything up to question 20. So 1 through 19 on the problem sets, well, at least my problem set anyway, you can do. So I would recommend starting some of them just for practice. You can maybe do it while it's still fresh in your brain today, or give yourself a break and come back later. But as always, you can email me with any questions you have. And if there's no last questions, then I guess I will see you on Monday, the 11th. Have a wonderful weekend. See you
You too.
later.